Good afternoon, everyone. We will explain the principles and application of fluorescence lifetime imaging spectroscopy. We're going to start from the basics of fluorescence lifetime spectroscopy and imaging, how the instrumentation records the measurements, advantages and limitations, and we're going to finish with data analysis and manipulations. So we're going to start with the basics of fluorescence lifetime spectroscopy and imaging. Firstly, the molecule will undergo excitation from the ground electron state S0 to the upper vibrational state of the first excited electron energy level, S1. After vibrational relaxation, the molecule will non-reactively relax to the vibrational ground state of S1. The molecule will return to the S0 through either a radioactive red or non-radioactively green pathway. So, fluorescence lifetime is the average time escalate between the activation of fluorophore and the elimination of the photon from the fluorophore. This is an important for the physical property, as it can provide useful insight into the energy, relaxation, and dynamics of the fluorophore. Fluorescence lifetime can be mathematically defined as this equation. One the molecular level, tau, is the average lifetime across a population of fluorescence is a random process. So now I'm going to describe you how the instrument obtains the measurements. So there are two main methods for measuring the fluorescence lifetime as a given example. First one is time domain method. It involves time-correlated single photon counting of fast-graded image in interspheres. Lifetime is calculated from the exponential feed to the decay data. The second one is frequency domain method. It obtains the lifetime through excitation of light or a pulsed intensity of a certain frequency. Included fluorescence elimination will show a delay in the form of phase shift. The phase shift and modulation depth are directly dependent on fluorescence lifetime and no modulation frequency. Extracting phase shift from elimination signal requires a homodyne detection method. So, the time-correlated single photon counting records each event in fluorescence decay. Either the timing of the pulsed acceleration source, like a laser or LED, with the timing of the arrival of a single photons, a decorator can reconstruct the lifetime decay over many events. This technique is based on the probability of detecting a single photon at a time. T after an exciting plus is protonational of the fluorescence intensity at time t. So you can see the equation below. In fluorescence lifetime imaging microscopy, the fluorescence decay is measured in each pixel of an image. After a lifetime is attained for each pixel, a fluorescence lifetime imaging microscopy image can be created by assigning a false color scale to the lifetime of each pixel.
The advantages and limitations of fluorescence lifetime imaging spectroscopy vary between the different methods and, more significantly, the level of machinery used. However, there are some underlying themes between all of these. The main common advantage of using this method is simply a fast acquisition speed, which is also highly accurate, and cannot be affected by other sources of light. These come as a result of this method's ability to distinguish between spectral overlap fluorophores, fluorophore morphing, through its capacity of determining fluorescent lifetime of the fluorophores. Compared to a similar method such as NAD pH spectrophotometer, the fluorescent lifetime imaging spectroscopy method is far superior. As within NAD pH, intensities from the fluorophores result in an overlap which cannot be separated. This chemistry makes the film method being significantly more accurate, as it allows for the acquisition of the data to be more concise and more efficient. On the other hand, even though this system of analysis is far greater than others, it comes with significant limitations, most importantly, the cost. This method is significantly more expensive to run and buy, yet even bought, there are still limitations to the system. As the system is so sensitive to be influenced by the surrounding temperature, pH, of the sample, and even the viscosity, which can dramatically alter the results of the analysis. This also means that the photon count has to be exact, as a photon count too high can give invalid readings, depending on the viscosity. However, this is also true for the counter. As if the proton count is too low, the data shown will be poor. This Goldilocks zone, or where the spectra can be obtained from, is also somewhere off being perfect. This is because the acquisition of the spectra is still slow enough for some fluorophores not to be detected. This, as a result, is that the detection isn't able to detect fluorophores with a short half-life, which can potentially mean be cancerous in biological organisms. This also means that dynamic samples are harder to analyze, as the changing environments that are within the biological samples are greater risk of being analyzed poorly. The graph to the right shows the data analysis from one of the most common methods of fluorescent lifetime imaging spectroscopy. The TCSP method utilizes a method called reverse TAC, which essentially measures the time between photon emission and then the next excited proton. This time-dominant method is prominent across all variant methods of fluorescent lifetime imaging spectroscopy. However, the quantitative analysis provides insights into cell function, heterogeneity, and other structural and functional biological features. Through techniques like the curve fitting, phase analysis, and deconvolution analysis, we're able to extrapolate the data obtained and further analyze it. However, the most important method for data analysis has to be machine learning analysis, which has become increasingly popular in recent years, as it provides the capacity to self-analyze all the data provided by the spectrometer using a few key algorithms. Currently, the main one used is called convolutional neuron networks, which rapidly calculate fluorescence lifetimes of the fluorophores and make highly accurate predictions on the dynamics fluorophore lifetimes within biological features.